This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good morning. Good morning. Thank you. Welcome to the Bankhead Theater, and thank you for coming for the second of 4 Science on Saturday presentations. Lawrence Livermore National Laboratory produces these science productions with the help of local educators. So a big thank you to the lab and the production staff. Our topic today is the extreme X-ray universe, discovery science with NASA's NuSTAR mission. NuSTAR will offer opportunities for a broad range of science investigations ranging from probing cosmic ray origins to studying the extreme physics around collapsed stars to mapping microflares on the surface of the sun. Now, does everybody understand what that means? Awesome, because you're going to learn about what it means today. Dr. Michael Pivaroff, William Craig, and Granada AP Physics teacher Tom Scheffler will address the innovative instrumentation on board and discuss some of the exciting science results from the NuSTAR's mission. Dr. Pivaroff developed instrumentation for NASA's Chandra X-ray Observatory and studied the X-ray emissions from neutron stars. He's the Associate Program Leader for the Space Systems and Enabling Technologies and an Associate Division Leader in Physics, where he leads the Applied Physics section at the Livermore Lab. Bill Craig is an astrophysicist also with the Livermore National Laboratory and at UC Berkeley Space Sciences Laboratory. He is the payload manager on the NuSTAR Telescope, and his interests are in the explosions that mark the end of the life of giant stars. Tom Scheffler received his Master of Arts degree in astronomy and astrophysics from the University of California at Berkeley, and during his graduate studies he fell in love with teaching and entered the teaching profession in 2002 and teaches at physics and calculus at Granada High School here in Livermore, and we're lucky to have him. So please welcome Michael, Bill, and Tom. Thank you.
Okay, great. So thanks, Chuck. So thanks to all of you for coming out today. We'll talk through some technology, we'll talk through some science today, and hopefully at the end of it you'll know a little bit more about what we call X-ray astrophysics than you did coming in. Before I start though, let me say that a mission such as NuSTAR, although it's small by NASA terms, it's big by anybody else's terms. It's $150 million, $160 million worth of hardware in space, and so that took a lot of people. Lawrence Livermore did a lot of the key technology on the telescopes, and you'll hear more about that later. But the mission was funded by NASA and is led by Caltech along with the Jet Propulsion Laboratory. So NuSTAR stands for the Nuclear Spectroscopic Telescope Array. It's a NASA satellite launched in June to study black holes and other celestial objects. And you'll hear about what kind of celestial objects we're looking at as we go through the story today. So what are we going to learn? First, what do we mean? What do we look at when we say high-energy X-ray astronomy? You know what a regular astronomer is, peering through a telescope looking at a star. So the astronomers that do high-energy X-rays they'll do it a little bit different way, and you'll learn something about that. You'll learn a little bit about the technology it takes to look at high-energy X-rays, or these kind of objects. And we hope you'll learn that why black holes are particularly cool to look at, because that's why I started doing this. And the black holes are not only interesting in their physics, they also tell us a lot about the universe around us. So everybody has a view of a black hole, a sort of a common view of black holes. And we'll start with sort of, if you like, a simple view of black holes, although I have to point out as we go through this that some of the physics are right. You'll see material being expanded as it gets close to a black hole, stretched out by the gravitational tidal forces. But we'll start here and hopefully go ahead.
Captain's log. Emergency report. We are fast being sucked into the hideous vortex of a black hole. Our rocket engines are useless. We are trying everything, even manual override. But to no avail. Our shipboard computer suggests one last alternative.
So there you go, all you need to know about black holes. So we look at black holes for a particular reason in X and gamma rays. And so let's start just with a quick primer. You remember this maybe from some of your courses, but what are X and gamma rays? So the electromagnetic spectrum is shown here at the top. And you see that from going from the radio through the microwave, the infrared, the visible, where we see, through the ultraviolet, X-ray, and gamma ray, as the wavelength gets shorter, and we have different names for it. This top bar is where we penetrate the Earth's atmosphere. And of course, we can do that in the visible, and that's good because we need the light from the sun to keep us warm as well as to grow food on Earth. But as you get higher energy than that, actually the light interacts with the atmosphere, doesn't make it all the way through. Well, that's good because otherwise we'd be irradiated and dead. But it makes it hard to do X-ray astronomy. And in fact, X-ray astronomy didn't start until the age of rockets. And in particular, it's very hard to do when you get to very high energy X-rays where the wavelengths are down below the size of an atom. So you really have to trick these X-rays to make them do what you want. And we'll learn about the technology that does that. Now, as you go down this chart, you see both the size scale of the radiation, but you also see its temperature at the very bottom here. And so what we're looking at is down in this region where things aren't million degrees. They're up to 10 million or even hotter in temperature. Very, very hot, much hotter than the surface of the sun. So that's the type of energy we're looking at. And you could ask, well, why study it? Well, I told you can look at black holes and other exotic objects. But if you look out in the optical, visible with a regular telescope, the universe is pretty peaceful. You've seen the skies twinkling. During the summer, you can see the plane of the Milky Way, and it's all rather copacetic. Looks like nothing's changing. If you look in the X and gamma ray, on the other hand, you're looking at a very violent place. You're looking at things colliding, things annihilating, huge amounts of energy being emitted in short periods of time, and of course you're looking at things that are millions of degrees in temperature. So a much more violent place, but for me a much more interesting place. So how do you study X and gamma rays? Well, number one, because they don't penetrate the atmosphere, you need to get above the Earth's atmosphere. You also need new technology. It's very hard to take these pieces of radiation, these particles of radiation, these waves, and focus them to a point to make a picture. So we have to invent new technology to do that. And I've been doing that, give or take, off and on now for 20 years, trying to figure out how to take pictures, how to look very deeply and very sensitively at these wavelengths. Now, in terms of getting above the atmosphere, the way we do it at first is we use high-altitude scientific balloons. And you can see a picture of that here. This is a 300-foot tall balloon stack. There's a little bunch of helium at the top and an experiment at the bottom of that train. That experiment, in this case, is about 20 feet tall, to give you some idea of scale. This balloon will, when it gets up to about 40 kilometers, 25 miles up, it'll be the size of a football stadium. But it's all contained in a plastic bag no thicker than a garbage bag you might use at home. These are pretty amazing things, and they get us above 99% of the atmosphere, and they help us try out technology and do a little bit of science. But they don't last very long. We can only stay up there a day, maybe a few days. And that doesn't give us enough time to look at what we want to look at. So although we started with this technology on balloons, we wanted to move them onto satellites. But to do that, we really had to demonstrate we knew what we were talking about. And we've been working on a program to do that for the last couple of decades. And I started that with Mike Pivovarov, who will talk next about how this technology works. And I'll actually start by telling you something about exploding stars, and then we'll work on through there, and then I'll come back and tell you more about the NuSTAR mission. So thanks.
Thanks. So before we get into the technology, we wanted to try to motivate some of the science that we would like to do with NuSTAR. And so we wanted to start with the endpoints of stellar life, and that's with exploding stars. And so the thing to remember is there's two major forces going on in every star, just like our sun. There's gravity trying to squeeze all of the material that's in the star down, and then there's radiation pressure pushing outwards. And there's a nice animation here we'll show you. And that radiation pressure comes from fusion. So in our sun, hydrogen is being fused into helium. And so the animation is showing as you're burning the hydrogen is decreasing, and then you have helium ash, that starts to burn. So you have radiation pressure, so the star is still in equilibrium. You then have helium ash, that starts to burn, and you'll see this sequence as more and more elements are formed, burning's going on, but at some point, once you hit iron, you can no longer burn iron and support that star, so it collapses upon itself, so that's gravity winning, and then you have this massive explosion and material jetting out at thousands of kilometers a second. And so we have Tom now who's going to give a very nice demonstration of how that energy transfer happens and how that explosion occurs.
Talk about explosions. You might be wondering, how does this implosion, this collapse of the core, turn into an explosion? And it all has to do with conservation of energy. So we're going to represent the imploding core of a star with this basketball and the lighter weight outer layers of the star with this tennis ball. So if I hold the basketball and the tennis ball like this, above the ground, they right now have gravitational potential energy. If I let go, they're both going to fall. This potential energy is going to turn into kinetic energy, energy of motion. And this falling is representing the collapse of the iron core of the star. When the collapse halts, that will be the basketball hitting the ground. When it hits the ground, it's going to rebound and then smack into the tennis ball. And what's going to happen is you're going to have all of what was potential energy of the entire mass being given as kinetic energy to the mass that was sitting on top.
So you have this explosion, and there's two things that are left over. So those outer layers, represented by the tennis ball, that becomes something we call a supernova remnant. And that's shown on the image on the left. So this is actually a star that exploded a little more than 300 years ago. And this image was taken with the Chandra X-ray Observatory, which looks in the soft X-ray or lower energy part of the spectrum. And the different colors represent different elements. And the way this works is, some of you may have seen this if you take various gases or elements and put it in a flame in the laboratory, you'll see different colors of optical light, reds and greens and yellows in different ratios. So each element has its own unique spectral signature. And it's the same thing happens in the X-ray part of the spectrum. So the yellows and oranges and greens in this image represent different elements. So we see silicon, magnesium, calcium, all churned up in that exploding outer layers. And again, this material is moving out at incredibly fast speeds. And this supernova remnant is billions and billions of kilometers across. So it's a massive object. On the other side, you have the burnt out cinder of the star. That's going to likely be a neutron star or a black hole. So in the image on the left, right in the center, it might be a little hard to see, right here, that little dot, that we think is a neutron star. And so the image on the right is an X-ray image of a neutron star, and the reason we can see X-rays from that neutron star is because it's very hot, so it glows in the X-rays, and there's a lot of exotic physics going on, extreme physics, and so we're getting a lot of X-ray radiation from non-thermal mechanisms as well. The neutron star is only about 10 kilometers in radius, so you have massive differences in the size scale. And a good way to think about this is the fireworks that we all enjoy on the 4th of July. So before that explosion, what happens is you pack gunpowder and other things inside a very small cardboard shell. So that's a healthy star. It's in equilibrium. It gets shot up into the air, and it explodes. So the fireworks that we enjoy, that's kind of like the supernova remnant. And then what's left over is that cardboard shell. That doesn't go away completely. There's some piece of it left, that's cinder, and that's the stellar endpoint. That's the stellar remnant, which could be a neutron star or a black hole. So it's pretty interesting to think, okay, so you've got this stuff going on out in space, but what does that have to do with me? Well, we know that hydrogen and helium was made at the very beginning of the universe, in the Big Bang. But those lighter elements we saw from that animation come from fusion that's going on in suns and stars. But the way that material gets spread out is through that supernova explosion process. So I'd ask any of you that have coins in your pocket or maybe your purse to pull those out and look at those. So your nickels, your dimes, your quarters, your pennies, and they don't look like very exciting, interesting objects, but all of that material, the copper, the zinc, the nickel that's in your coins, all of that came from a star that exploded. So our entire solar system is star stuff. So it's that stellar explosions. It gets redistributed, it coalesces into solar systems, and that is from an exploding star. Same thing for the calcium in your bones or the aluminum that is in the can of your favorite beverage, all from stars. So I mentioned that one endpoint after the star explodes is a neutron star. The ones that are even more exciting are black holes. And that happens when the mass of the star is maybe 10 to 100 times the size of our sun. So very massive stars, when they die and explode, you wind up with a black hole. And it's very interesting. The extreme gravity provides the energy that it can accelerate particles to nearly the speed of light, and you get all of these interesting X-ray phenomena that we can see with NuSTAR. So we saw the Ren and Stimpy cartoon. A black hole isn't just a vacuum cleaner. So a good way to think about this, if you were to take our sun and replace it with, you could squeeze it all down, it could form a black hole. Two things would happen. So first, life on Earth would end because there'd be no starlight. That would be bad. But the planets themselves would continue orbiting around that point-like black hole. And that's because it's just mass. It's only when you get very close to the black hole that you experience those tidal disruptions. And if it gets heavy enough, if you put enough mass into that black hole, nothing can escape. And Tom has a very nice demonstration here to walk you through some of the physics of warping and what's going on with black holes and gravities.
An equation for gravity, and he was able to calculate very well using his law of universal gravitation. What is the force of the Earth on a falling apple? What is the force of the Earth that keeps the moon in orbit around the Earth? And while Newton was able to calculate very well how strong gravity is, Newton was the first to admit he had no idea why does gravity happen. How does the apple know the Earth is down there and it should fall that way? How does the moon know that Earth is over here and it should keep circling it? And the first person to really come up with an explanation for why does gravity even exist was Albert Einstein in his famous theory of general relativity. Einstein's explanation involved thinking of space itself not as just an empty vacuum, but as almost like a fabric, something that could be stretched and warped. So what we have here is a stretched piece of just spandex, and this would represent empty vacuum of space. There's nothing in it. You put some mass in it, and that mass is going to literally stretch the fabric of space nearby. If I put another mass, it will also warp the nearby space, and the two masses feel each other's warped space, and the two masses gravitate toward each other. So this is what gravity is. It is objects following curved space warped by the presence of mass itself. The more massive the object, the greater the stretching, the greater the warping. So if I put more mass here, I'm going to get an even larger dent, a larger warp in space. If I put an object right here, maybe that's the Earth, this is an apple, and the apple falls because it is occupying space that is curved and warped, and it follows that warp, that curvature that was created by the presence of the mass. Now, fortunately for us, even though, say, the sun is exerting a gravitational force on the Earth because of warping the fabric of space in our solar system, Earth is not falling into the sun. Earth has some sideways motion too. And so this same effect can lead to a circular orbit. Now, unlike the marble rolling on the spandex, there's no friction between the Earth and space, so we're not going to be spiraling into the sun anytime soon, which is... But not all orbits are perfect circles. Some comets, for example, have pretty elliptical orbits, so we can do something like that. And the Earth itself exerts some gravity, and we have a moon that feels that gravity, and hopefully I can get this to work. If you roll this just right, we can see the moon orbiting the Earth. There it goes. Let's try that one more time. And what a black hole does, a black hole is an object that has so much gravity that it warps space and time so much that it is literally a bottomless hole. Imagine this being stretched, and it goes stretched downward forever. So a black hole is literally a hole in the fabric of space and time.
Thank you, Tom. So we saw the cartoon rendition of what happens as you go towards the center of a black hole, and this animation gives a little more scientific feel to things. So we know that black holes are at the center of every galaxy. So this is an image of a spiral galaxy, very much like our own Milky Way, and we're going to quickly move from the outer regions into the center. So we're moving around, we're getting closer to that region. All of the stars in the outer arms are in very stable, benign orbits. And as we get closer, you have swirling gas in something called an accretion disk. And due to friction, that material is going to fall into the black hole. And as you get closer and closer to the black hole, it's spinning more and more rapidly. You're getting those tidal distortions. So the cartoon showed that spaceship and Ren and Stimpy being stretched out. That's really happening as you get very close to the black hole. And a little more details about black hole structure. There's something that's referred to as the event horizon. This is the technical term for that is the Schwarzschild radius. And this has to do with the mass of the black hole. So the more mass that's in the black hole, the larger is the Schwarzschild radius. So an example of this is if you were to take our sun and squeeze it into a black hole, it would be 9 millimeters in radius. If you were to take our Earth and squeeze it, that was our Earth, would be 9 millimeters. Our sun would be about 3 kilometers, so the size of downtown Livermore. So really, really dense, very small objects. And the interesting thing is once something gets inside the event horizon, it basically disappears forever. And that includes light. So nothing, once it falls inside the event horizon, can escape. And that includes information. So it's a little bit like those ads you see on TV about Las Vegas. Whatever happens inside a black hole stays inside the black hole. So there can be lots of theories about it. It's great for science fiction, but we have no way of knowing what goes on. And we're going to come back to this term, the Schwarzschild radius, a little later on in the talk. One of the important things to remember is there's basically 3 pieces of information we can know about black holes. We can know their mass, we can know their charge, and we can know whether or not it's spinning. And right now, the only thing we've been able to conclusively measure about black holes are their mass. And I'll show you how we do that in a second. But first, we want to talk to you a little bit about the technology we need to image X-rays. So it turns out that if you have the right conditions, you can make X-ray mirrors. And so normally what would happen is you have X-rays impinging or hitting a surface, and they're going to just be absorbed by that surface. And if you change the angles at which the X-rays are hitting that surface and make them shallower and shallower, at some point there's a transition from when the pink rays are showing X-rays coming in, they're being absorbed. But if you make them operate at maybe a degree or less, then they'll actually be reflected out. And so that's what's illustrated here by the blue X-ray rays. And so this is it's very analogous. You can do this at home right now with a flashlight and take the mirror that's in your bathroom. And if you shine your flashlight at an oblique angle, at a grazing angle into the mirror, that flashlight's going to bounce off the mirror at the same angle, or the same angle that it comes in at the mirror is going to bounce out. So that's the same thing that's going on with X-rays. This works very well at the soft or lower energy part of the X-ray spectrum. To make these mirrors work at the high energy part of the spectrum that we are interested in, you have to have special layers on top of this mirror substrate. So we use glass substrates, and we put on these multi-layers or nanolayer structures on top. For NuSTAR, we use alternating layers of platinum and carbon. So what you see on the right is a TEM, a transmission electron microscope image through one of our special coatings. And you see hundreds of layers of alternating amounts of platinum and carbon. And in the thinnest, these structures are all of a few nanometers thick. So these are highly engineered structures, and it lets us make very good high energy X-ray mirrors. And to make a telescope, we want to be able to collect a lot of light to be able to see these very faint, distant objects across the universe. And the way we do that is we nest mirrors inside one another. So a simple X-ray telescope would basically be a barrel with these special layers on the inside of that. To build up area, we nest them inside one another, the same way that you can nest Russian dolls, those little toys that fit inside one another. So that's what we do for NuSTAR. We actually have 133 of these X-ray mirrors in the shape of barrels that fit inside one another. And that's shown here on the image on the right. This is actually one of our NuSTAR telescopes. And you can see that this very thin glass, less than a millimeter thick, has these special coatings on it. And we assemble those together, and that's what forms our X-ray telescopes. Now, I mentioned before that we have some idea of what the mass of black holes are. And there's this very beautiful measurement that's been done over the course of 15 years by Professor Getz at UCLA. And she and her team have been looking at stars in the visible and infrared very close to the center of our own galaxy. And it's this very nice image here. And so what you'll start to see is the paths of the stars. They rotate around the very center of our galaxy. And you see that they take very different types of orbits. So some of them are circular, like those first marbles that Tom had on the blue sheet. Some of them are highly elliptical, and so you see very fast motion as it gets close to that central object. And what we know from working on some math, we have an idea of what the mass of the stars are from the light they emit. You can infer what the mass of the black hole is at that center of the center of our galaxy, and that's 4 million times the mass of our sun. We know that in some cases, in other galaxies, the black hole at the center of the universe, the center of the galaxy is 1 billion times the mass of our sun. So the black hole we have in the Milky Way is kind of on the wimpy side. So the final thing, just to drive home how these X-ray mirrors work, is there's this nice animation which shows X-rays impinging on a typical visible light telescope, like a Cassegrain telescope. So the X-rays would just be absorbed. But if we go to this glancing incidence geometry, these barrels, then you can see the X-rays bounce off of the mirrors and get focused to a very small point. We put several of those mirrors together. We nest them inside one another. That lets us collect more X-ray light and build up a very nice image of what's going on. And so this illustrates the state of the art as it was 5 years ago and as it is now with the launch of NuSTAR. So on the left, this integral spacecraft was built and launched by the European Space Agency. It's still up It's still working. It was launched in 2000. And it uses a technique called shadow cameras. And it's basically you have a piece of lead, and you poke holes in that lead, and so the X-rays are either blocked or pass through that mask, and it creates a shadow on the detector. So through some very complex techniques, you can get an idea of what the distribution of X-rays in the sky are. And this is the same exact technology that Bill and I worked on 20 years ago for that balloon he was talking about. And now what we've been able to do with NuSTAR is make true focusing optics. So instead of using these masks, we can directly image what's going on in the X-rays across the universe. And so now Bill's going to tell you more about the NuSTAR Telescope and the deployment sequence. Thank you.
Hey, thanks, Mike. So that was a great description of the technology that it took to design, put together this kind of telescope. I'll take you through over the next few minutes over what we did to bring something together that actually allows us to take the images, and then we'll see some of the first images from NuSTAR. So you see NuSTAR in the upper right-hand corner of this picture. This is an artist's rendition. We don't actually have a picture of it on orbit. But you can see that it has two sides to it. One of them contains the optics. That's on the far right side here, where you see two barrels, if you like. And that's what contains the X-ray mirrors that Mike was talking about. Down here, way far away, about 30 feet away, are the detectors. And think of them like CCD cameras, just like you've got in your phone or in your camera. They take the pictures of the X-rays as they come in on the focus. And then everything else down there supports moving around this telescope around on the sky. There's a solar power to generate power, and there's radios and all sorts of fancy technology. But we can't launch something the size of a school bus. Well, we could, but it would cost us close to $1 billion, so we don't want to do that. We need to pack it into something much, much smaller. And that was actually the challenge for NuSTAR. What you see here is NuSTAR being put inside the nose cone of a rocket. It's a very small rocket, the smallest rocket NASA flies. In fact, it's small enough to bolt to the belly of an aircraft, and we'll see that in a minute. But here it is being packaged inside the nose cone, and you can see this reflective surface. That's one of the two optics. The other is hidden behind the half of the nose cone that's in place. And so the technicians lock this nose cone into place, roll it outside, and bolt it onto the belly of an aircraft. And what you see here is the NuSTAR rocket bolted to the bottom of an L-1011. Here's the rocket at the bottom of the aircraft here, as you can see. The nose cone is off to the very left-hand side of this image, and that's NuSTAR in there. It's about 6 feet tall and sits in the nose of this. The rest of this is all fuel to get it to orbit. Now, the advantage of launching with a rocket that bolts to an airplane is that you can launch from anywhere. So you can take off and you can fly to wherever you want to go. But now you have the problem of what do you do with the airplane, because you don't want to launch it with the airplane attached. That would be unfortunate. So there's a sequence that we go through, and you can see first the aircraft taking off, and it takes off in our case from a small atoll in the South Pacific called Kwajalein Atoll, which other Livermore work happens at, but this is the first time we've been to launching civilian space missions there. It's a very desolate atoll. It's very humid, very wet, and there's nothing to do. Particularly when you have to spend several weeks there, I can attest to that. But eventually you get to the day where you're going to launch, and with the aircraft, we actually launched at night, and you can see a series of images here from the belly of the aircraft. The first one to the left here is showing the rocket just before it's dropped. Then it drops for 5 seconds. And it has to do that to allow the aircraft to get out of the way. But it's a long 5 seconds because you're at 40,000 feet and you drop over 5 seconds, an awful lot through the atmosphere. And you have to remember that's something we've worked on for 20 years, and it's in free fall. And we're kind of hoping the rocket will light, and in our case, we were lucky, and it did. And so it moved to the first stage, ignited, and about 3 minutes later, the second stage, the first stage dropped away, and the second stage ignited. And in about 5 minutes, the whole thing was in orbit around the Earth. We separated from the last part of the rocket, deployed the solar array, turned on our radios, and it turned out everything worked and everything checked out all right. So after we did all our engineering checks, we had the satellite on orbit. Here you see it with the solar array extended, but it's still too small. Mike told you how the X-ray optics work. They can bend the X-rays, but they can only bend them a little bit. So it takes a long time for them to come to focus. That's why we need the 30-foot distance between the optics and the cameras. So we had to come up with some scheme to separate these by 33 feet. And what you'll see here is an animation of that happening. Before we go all the way through it, I want to show you a few features. Again, we talked about the two optics. These two barrels at the top contain all the X-ray optics that focus the X-rays. Down here below, you see this silver cylinder. That's one of two detectors, one of the two cameras that detects the X-rays and takes our pictures. And there's other technology as well. A laser up here which points to a little object down here, a little detector, because it turns out, although we can separate these two things, they move around as we move around the Earth, and we have to track the distance between them and the separation and the angle. And there's star trackers and all sorts of other fancy technology. But the coolest part of this is taking something that weighs about 20 pounds and stacks in something maybe 18 inches tall and turns into a 33-foot long, very stiff beam. And you can see that happening in this animation. Out of the base of this cylinder, you see a series of 4,000 little sticks, cables, and wires driven by a motor extruding out of this, like a transformer, if you like, turning from something that's one shape into a shape that's much, much longer. Turns into something, in fact, 30 feet long that separates the optics from the detectors. And without that, this wouldn't have worked. So we went through a 27-minute sequence, making sure that each one of these individual parts snapped into place correctly. And once we were done, we could turn the telescopes on and see if it focused. So we made this launch happen in the middle of June 2012. And it took us about 6 weeks to get everything checked out and turned on, and routine science operations began in August of this year, just a few months ago. So what have we learned? What has NuSTAR taught us? Well, so far, up through last week, we've looked at 75 individual objects. So we've looked at supernova, like the ones that Mike and Tom showed you. Supernova remnants, the remnants of those explosions. These things called pulsars, which are rapidly rotating neutron stars. But especially we've looked at black holes, because NuSTAR is especially equipped because it has this energy capability to look at black holes. So what have we learned so far? Well, we'll learn a few of these lessons over the next few slides. It really has given us, though, at top level, the first detailed look ever at the high-energy universe. So you're going to see the next few pictures you'll see the first time anybody has seen these. We haven't been able to take these kind of pictures before, and they really, at least to me, are quite revealing. So to give you an example of what the improvement is, the panel to the left here shows a supernova remnant, one of these remnants of exploding stars, before NuSTAR, looking through one of these shadow mask imagers that Mike talked about. And what you could see is a dot, basically. There was a dot and there was something there. So the analog is, say, for example, you didn't have your glasses on and your eyes are bad, and you've got a book. You can open it up and you can see there's maybe words on the pages, but you have no idea what they mean. So that's where we were at. We knew there was information there, but we didn't know what it was telling us. The panel to the right is the NuSTAR image of that same supernova remnant. And what you see here is what we call low temperature for X-ray astrophysics. That's 2 million degrees. So you can see that in red light. So you can see blotches of red here where things are cooler than in other parts of the remnant. The green is at 4 million degrees, and the blue is at 10 million degrees. And you can see out at the periphery on the shell of the supernova remnant that there's very high energy things going on. Not close to the middle where the explosion happened, but out at the edge, which means something's happening, and there's an interaction between that blast wave and the material around it. So this is the first time we've been able to see it with this kind of detail and this energy. So that's supernova remnants, but as I said, we really like to look at black holes. And the best black hole for us is the nearest one. The nearest supermassive black hole, these million-mass black holes, is in the center of our own galaxy, in the center of the Milky Way. And so in August of this year, we put together a observing, what we call an observing campaign, where several telescopes are looking at the same place at the same time. This is an image of the two Keck telescopes on the summit of Mauna Kea. And out of each of those domes is coming a laser, which allows the light to be corrected, and they get very, very sharp optical imagery. And as many of you know, that laser light technology was developed in large part at Livermore over the last couple of decades and is now used at many telescopes around the world. But the two Keck telescopes were aiming at the galactic center. We were looking at the galactic center with NuSTAR, and a couple of other telescopes on orbit were also looking at it. Now, we were trying to calibrate, look at the different energy at different wavelengths. Because normally the black hole at the center of our galaxy is actually rather boring. It's got a sort of a common accretion rate. It's not really doing a whole lot. But we got lucky. We saw a flare at the center of the Milky Way, and let me walk you through that. What you see in the red is a picture of the Milky Way in the visible or the infrared, and you can see it's a rather pretty picture. There's something going on there in the middle. You see these dark clouds. That actually turns out to be clouds of dust and gas. And then there's an X-ray image, and here's the X-ray image. That's that black hole at the center of the galaxy steadily sucking in material. But while we were watching it over a couple of hour period, it brightened. It brightened very significantly, actually. So it got very many times brighter, and then it went away. So we saw a flare. So something happened in that flow. Could have been Ren and Stimpy, could have been something else. So we looked at what the cause could be. Well, you'd first think, well, you saw all those stars orbiting. Maybe one of them got too close and it disrupted that and ate it up. But it turns out that's not quite possible. The flare we saw wasn't bright enough. But we do believe that just like there's comets and asteroids in our solar system, they're there at the center of the galaxy as well. And you can see in these cartoons to the left what might happen. If you look at that one little dot there in the orange area, you'll see that it's gotten a little too close to the black hole, and it's in that portion of space-time where the fabric starts stretching, where you're getting a lot of distortion. And a few seconds later, it's distorted. It's stretched out just like that rocket ship was stretched out. And then shortly after that, boom, it hits the event horizon, and the material gets sucked into the black hole. And what we saw was the signature of that, the X-rays and gamma rays that were emitted as that thing happened. Now, that was an interesting thing, but there's a much more interesting thing coming. So it turns out in September of this year, the same people who did that very nice map of the stars going around the center of the galaxy, they've been tracking the clouds of dust and gas as well. And it turns out one of those is going to intersect that black hole in September of this year. There'll be a large event where this thing breaks up basically the molecular cloud and gas and sucks part of it into the black hole. So we'll be watching then, as will a bunch of other telescopes. It'll make the news at that time, but you heard it here first. So, all right, so you got a picture, a flavor of what NuSTAR is telling us. And I'm going to give you a complicated story, and this is a little harder. Don't worry too much about the details, but let me try to walk you through the story because I think it's a really cool one. As we know, galaxies have black holes. We've seen one in the middle of our galaxy. We think they exist in the middle of most galaxies. There's a number of lines of evidence which make us believe that. So we wanted to look at a galaxy very much like our own. It's a spiral galaxy, and you can see the spiral arms here. And we wanted to look at it simultaneously in low-energy X-rays and high-energy X-rays to see if we can stitch the physics together and tell us something going on about in the core of that galaxy. So we did observations of this particular galaxy. It has a name, NGC 1365, and we looked at it for 130,000 seconds. That's 86,000 seconds in a day, so a day and a half. We were watching this black hole with two different telescopes. And we finished that in August of 2012. What we were looking for was the emission down around the black hole. So if you remember back to what Mike was talking about, he talked about something called the Schwarzschild radius. So that's the radius of a black hole, if you like. That's where, if you're inside it, you're gone forever. If you're outside it, then we can still see you. So that's a Schwarzschild black hole. That assumes, though, that radius, and we can calculate what it is from the mass. That assumes that the black hole is not spinning. But we know things in the universe tend to spin. They tend to orbit. And as things come in, you see that accretion disk, things spin. So we think black holes must spin. We ought to be able to measure that. But it's really, really hard to do because you're looking at something that's very small, it's very far away, and these energies are very extreme. So don't worry too much about the details of this graph, but let me just say that if a black hole is a Schwarzschild black hole, it's going to have an innermost orbit, that is the orbit at which things could be stable, that's about yay big. Say it's as big as a beach ball. As it starts spinning, that radius comes in, and it gets much smaller. In fact, it can get as much as 6 times smaller. So from a beach ball, say, down to a softball size, depending on how much it spins. So how do you measure that? How do you know that's true? You can do the math, but now you've got to actually do the observation. So that's what we tried to do. And as we trace along this curve, we have a prediction about what it might look like. So NuSTAR takes these images, and I've shown you the pretty picture, but it also measures the energy of the light. And it gives us what we call a spectrum. Let's think of it as a fingerprint, an energy fingerprint. So there's a lot of explanations for what can come out of black holes, many of them fairly simple. There's stuff coming in, it's absorbed by dust and gas, and that's what we see. If the energy fingerprint from this particular black hole was due to a simple explanation, you'd see this purple fingerprint. And just look at the shape of it. You don't need to understand the details of it. But as we go to the right-hand side, higher in energy, we see it dip down. So if we look at this energy fingerprint and it's dipped down, then it's just a cloud of gas. It's interesting stuff. Things are getting sucked in, but nothing really is happening in the spin. However, it turns out you can calculate that if it's spinning, that energy fingerprint will be different. And not only is it different, it can actually tell you the shape of it, can tell you how different it is. That is how fast it's spinning. So if the light, this fingerprint shoots up as we go up in energy, then black hole spin's responsible for it. So we knew that going in. We had our little theories. And so we took the data. And what you see is that it goes up. And it actually matches, so the red lines here are the spin prediction, assuming that we have a maximal spin, and the white are the data. And it matches exactly what you would expect from a maximally spinning black hole. So this black hole is not only spinning, it's spinning as fast as it can theoretically. And that's the first time anybody's been able to do that at this wavelength, because we haven't had the technology before to do that. So anyway, black hole spin is only one of the things we're looking at. So we look for supernova remnants, we look for high energy emission, we look for the signatures of the creation of elements and the physics of how stars explode. We've talked a lot about the technology it takes to do this kind of science, and the thing to understand is it took 20 years of technology to development to go take 2 years of pictures. And the pictures will tell us a lot about the science, but it does take the technology to develop it as well. And then we've also learned that the massive black hole at the center of at least one galaxy, can't say it about all of them, but at least that galaxy is spinning, and it's spinning very fast. So we have a lot of surprises in front of us yet to come over the next few years, and this image here is actually just one of them. This picture shows an edge-on spiral galaxy, and these 2 cyan dots here are what we call ultraluminous X-ray sources, sources that emit X-rays so brightly we have no physical explanation for them. They're very, very bright sources, and we're starting to find those in many of the places we look. So we look forward to a lot of new discoveries over the next few years.
I think with that,
If you have more questions, just come on down to the front.